Number 25. Integrate sine of 6x times cos of 4x. Now these identities, trig identities, are on our calculus formula sheet here. And they are identities to how to handle the two different angles. Now I've seen people make the mistake before, of course this being the final, hopefully if you did, you corrected it now, but I've seen people like use these identities and they think that's the answer to the problem. It is not. The identity just converts it into a form where you can integrate it. Make it a little bit bigger. Okay. Yeah, so we have to integrate. After we use this identity, we have to integrate. These are pretty easy problems. It doesn't matter which one you call M, which one you call N. Be careful. If you get negatives, that's fine. If you want to reverse them to where they're not negative, you can do that. But you may recall the negative identities for trig functions. For example, sine of negative x is the same as negative sine of x. So for sine, the negative comes out. Not true for cosine. Cosine of negative x just equals cosine of x. Negative, positive. All right. Erase that. So this is pretty easy to plug and chug into this problem. So you just have a sine of 6 minus 4 x plus sine of 6 plus 4x with this 1/2 on the outside. So now you just integrate 1/2 sine of 2x plus sine of 10x. That's easy enough. Antiderivative of sine of any ax would just be negative 1 over a cosine of ax. So the antiderivative of sine of 2x is negative 1/2 cos of 2x, and then sine of 10x would be negative 1 over 10 cos of 10x, plus c with the 1/2. Now notice that the answers are in different order. I didn't go to the next step, but the next step's easy. It's just distributing the 1/2 through your answer. And then you actually have to reverse the order of the terms, but it matches answer C perfectly. All right, let's take a look at number 26. Integration by trig substitution. All right, these can be kind of challenging. I don't like for the problems on my final exam to be too complicated. I mean, the technique itself is complicated. I mean, I don't pick the hardest of the hardest ones. In other words, this one's okay, but you can really have some challenging ones. Same thing goes for partial fractions also. So I like to keep them nice and basic. And I consider this, but you see, it's still a lot of work even if it's basic. All right, we must convert everything that we get a triangle built, and then we have to convert everything over to trig functions. Now, your radical here has minus, so that means when it's minus between the two terms, you can put it either on the adjacent or the opposite side. When the radical has a plus, it can only go on the hypotenuse. So I put it down here on the adjacent side, and that means the hypotenuse will be the square root of the first term. Square root of 16 is 4, and the opposite will be the square root of x squared, which is x. And it certainly doesn't hurt, whenever I teach this class, face to face or video on this section itself. I would have said it there too, is always emphasize that it does not hurt to check Pythagorean theorem if you need to make sure your triangle's valid, because if your triangle's not right, anything you do after that's a waste of time. But I can clearly look at this. I mean, I'm not saying you have to do it in your head. I mean, write it out. But I can look at it and see that a squared plus b squared equals c squared. So that's what we're trying to check. And it does, so we're good. All right, so we always need to find x in terms of trig functions because dx comes from the derivative of x. So sine of theta equals x over 4. That means x equals 4 sine theta. The derivative then would be 4 cos theta d theta. And then if I let cosine be the radical over 4, that means the radical will equal 4 cos theta. Guess I can go through these a little faster than my lecture video where I've actually explained it the first time, but not super fast. But anyway, let's see what we have here. So the radical, which is 4 cos theta, and then we have dx, which is 4 cos theta d theta, so we multiply those two together, which gives me, I skipped a step here, but let me tell you what step I skipped. It's an easy one. Cosine times cosine would be cosine squared. So the identity for cosine squared theta, integrating identity, is 1 plus cosine of 2 theta over 2, 16 on the outside. 16 divided by 2 is 8. And so here we go. We have 1 plus cosine of 2 theta. The antiderivative of 1 would be theta. Antiderivative of cos of 2 theta would be 1/2 sine of 2 theta. And then we can't evaluate sine of 2 theta off of this triangle. We can only figure out functions of just theta. So we have to use a trig identity here where sine of 2 theta equals 2 sine theta cos theta. The 2's cancel. And theta is always going to be arc something. Now, of course, in a multiple choice format, you would see which one it was using. I'm assuming on your test it probably would have more answers than just one with the inverse here. That kind of gives it away. Don't assume you would only have one here, but it could really be lots of things. But you can tell by the answers. Usually it's the one that's the least complicated looking. So if sine of theta equals x over 4, it would make sense to call sine theta to be sine inverse of x over 4. That's what, or arc sine, either one. But yeah, you could use any one of the 6 trig functions. It could also be cosine inverse of square root of 16 minus x squared over 4. It's probably not what you would see in your choices. You'd see probably the inverse sine. So, and then what do we have here? Okay, for these two pieces, sine theta, cos theta, get them right off the triangle. We know sine of theta is x over 4. Cosine of theta is the radical over 4. And you just kind of combine all these terms to find the answer. Like I was saying a minute ago, this one's sort of a giveaway because it's the only one that has a sine inverse there, but let's pretend like it wasn't. Multiply those. Let's see, 8 divided by 4 times 4 would be 1/2, and then you just have x times the square root of 16 minus x squared, so it clearly does fit answer C. All right, let's try number 27. Another trig sub. Now the radical has minus. This time I put the radical on the opposite. What I usually do is what you don't have to do, because you could actually, you could start writing your things out there, and you could actually switch positions because there's always 2 and only 2 correct triangles you can make. And the second one is always flipping the opposite and the adjacent. Whatever the hypotenuse is supposed to be, that's what it has to be. It can't change. This always works better for me for some reason whenever, unlike the last problem, minus whenever the x is in front, where the last one, 16, was in front, I put it on the opposite side. And that seems to work for me. And like I was saying, you could change your mind if you wanted to. If you were getting like secants and cosecants, instead of cotangents and cosecants, and you didn't want to mess with integrating those functions, that's what you could switch it and then do that way if you wanted to, and if you felt more comfortable with tans and secs. We generally work more with tans and secs than we do cosecant, cotangent. So let's see what we have here. So that means the hypotenuse will be the square root of x squared, which is x. The other side will be the square root of 4, which is 2. And that does satisfy Pythagorean theorem. So I'm going to use the radical over 2, which is tan theta. So therefore, when you move the 2 tan theta will be the square root of x squared minus 4. Kind of skipped a couple little steps here. Not major steps, but secant of theta equals x over 2. Therefore, 2 sec theta equals x. And let's see. Therefore, now we need the dx. So the derivative of that would be 2 sec theta tan theta d theta equals dx. So now let's put our integral together based on these pieces here in green. The radical in the numerator, that is 2 tan theta. The x on the bottom, 2 sec theta. Dx on top, 2 sec theta tan theta. So you see there's a 2 sec theta that cancels. And we are left with 2 tan squared. So obviously obviously you didn't have to do this, but I pulled the 2 outside the integral. And to integrate tan squared, you have to use the identity sec squared minus 1, because we can integrate sec squared very easily. That's why. So that's probably the trickiest part about this problem is realizing what to do with tan squared. And once you know it's this, the rest of it's not too bad. So the antiderivative of sec squared is tangent, and the antiderivative of 1 is theta. And you see I distributed the 2 to both terms. So 2 tan theta is defined as the square root of x squared minus 4. And then if sec theta equals x over 2, we used inverse secant for this one. So therefore, it would be 2 inverse secant. And you can see by the answer. Well, there's an inverse sign there also. It's not right, but I mean, at least you could see that which ones you were kind of working with here. So and they left the 2 factored out. Okay, well, that's fine. I distributed it, but obviously answer D is still correct. So I guess maybe the way to do it would be to leave the 2 factored out, or check your answers, then see if you need to distribute it. So I guess maybe I jumped the gun. I mean, obviously I was right, but I mean, okay, we can all learn something here, I guess. But that one worked out okay. Okay, here's another fun one. Dx divided by x squared plus 25 to the 3/2. Now this will give people problems every once in a while, because they will want to put this x squared plus 25 to the 3/2 on the triangle itself, which is absolutely positively incorrect. You can only have square roots on this triangle. That wouldn't satisfy Pythagorean theorem. Well, I guess it depends on how you labeled some of the other sides, but still, we don't want to get into that. Let's just say it won't satisfy Pythagorean theorem with x being one of your sides. Put it that way. So, we're going to just treat it as the square root, and then what we'll do is we'll raise the square root to get it to be 3/2. So you raise the square root up to whatever power you need. All right, so this is a plus, so that means the radical has to go on the hypotenuse, and then you can interchange these 2 sides if you want to, but one of them has to be the square root of x squared, which is x, and the other one has to be the square root of 25, which is 5. And so there we go. We have a triangle built. So tan of theta would be x over 5. Therefore, x equals 5 tan theta. And then the derivative then would be 5 sec squared theta d theta. And then the radical divided by 5 would be secant theta. So you move the 5 over, 5 sec theta then equals that radical. And we have everything we need. So here's what so the numerator is going to be dx, which is 5 sec squared theta d theta. So now here's how we take care of our 3/2. We just raise the radical to cube, third power. In other words, the square root of something cubed is 3/2 power. Interesting. So there we go. Now we have it. So there's actually a 1 5 on top, and there's 3 5s on the bottom. That's how I get 1 over 25. But you obviously use a calculator for that if you need to. I'm more interested in the trig part of this. I mean, we got to get the number part right too, but still, you could figure that out pretty easily. But let me get back to this. So I have secant squared over secant cubed, which is secant on the bottom. And one of the rules I talked about before in my notes is that you never integrate 1 over a trig function. 1 over sine, 1 over cosine, 1 over secant. You never integrate that. Some people will look at this and call that natural log of secant. And that would be absolutely wrong. But so you just bring it up and write it as its reciprocal trig function. So 1 over secant's actually cosine. Well, then this one turns out to be pretty easy after all. Sometimes you can just never tell about these trig substitution problems, as it might look complicated, and sometimes they turn out to be kind of easy. Never want to say too easy, because they're not easy, but they're not overly complicated. So we just have the integral of cosine, which is sine. So we have 1/25th sine of theta. So sine of theta on my triangle would be opposite over hypotenuse, so it'll be x over the square root of x squared plus 25, 1 over 25 in front, and that looks exactly like answer B if you distribute 25 through there. Or not distribute, but get rid of the parentheses. So definitely answer B. All right, now partial fractions. These can get a little messy. But obviously the first and foremost important thing here is that you set up the format of decomposing it properly. If you don't do that, anything else after that gets kind of ugly. A little bit bigger. Now this is going to have 4 terms. And as we learned before, it doesn't matter which order they're in. As long as we know there's 4 of them. See, x squared by itself is what's called a repeated linear factor. So it requires an x squared and an x, 2 separate fractions there. X squared minus 25 factors into x minus 5, x plus 5, so they each get their own fraction. So there's where you have 4 terms. But like I said, they could be in any order. A, B, C, D over any of those fractions. As long as you do it right, you'll get the correct numbers. Well, okay, I did this way. You might, like I say, if you look at my notes and you want to use matrices to solve these, that's certainly not a bad idea if you feel comfortable doing that. This, I'll show you this method. Matrices, I would have to have a little more information kind of worked out first, though. So, but this method's not too bad here. So obviously the first step is you're multiplying everything by the LCM, which is on the bottom of the left side. So you're always clearing out the left side, so it leaves 1. And then the right side, we write whatever's left after. All denominators are going away so as you multiply. But on the right side, it's just a matter of what's left up in the numerator with each part there. So I'm not going to read all these. You can read these. So they're coming from with what's left here. So I chose this way to do it. Like I said, it didn't take me too long doing it this way. So if you come through here and let x equals 0, that's wiping out B, C, and D, because they all have an x in there. And we can solve for a, so you get 1 equals negative 5 times 5, which is negative 25. So a equals negative 1 over 25. And if you use 5 for x, you can get rid of a, b, and d and solve for c. So you put 5 in there on the right side, you'll get 250c equals 1. So therefore c would be 1 over 250. And negative 5 gets rid of a, b, and c, and enables me to solve for d. I get negative 1 over 250. So the only thing I need to get here correctly is b. Now what I did here, I said I multiplied by 250. That's because to get b, I'm going to be putting in the values for a, c, and d. So just imagine here for a second that the a, c, and d are plugged in right here. There's a, there's c, there's d. So you multiply everything by 250. So you see the b part turns into 250, but this one, 250 divided by 25 makes 10. I'm just ignoring the negative sign for now, but it's there. And then here, you see, you multiply by 250, c would have been 1 over 250, but it would go away. You multiply by 250, and same thing for the d, even though it's a negative, but yeah. So that's what happened here. If you just plug in the ACD, multiply by 250, and we actually get b equals 0, which that can happen. You can get a term to zero out every once in a while. I'm not saying you should expect to see that, but it can certainly happen. So let's see what we have here. Like I said, usually the least difficult part about this is the integration, because it ends up being basically either power rule, natural log, or some sort of arctan, might be really the only things we're kind of looking for. So now you see that, so B is gone, so we have to rewrite this as there's A, there's C, there's D. Of course, you can pull for some reason, I don't know why I put unless I was just trying to make it match the maple answer there. But anyway, that's just the decomposition for maple. That's not the integral. That's just each of the coefficients. Well, okay, whatever case is, I rearranged them. I don't know why, but I have the D in front, so D, but I have the right number there. So it's negative 1 over 250, 1 over x plus 5. I just pulled it outside the integral. And then the xa over x squared is the same thing as x to the negative 2, and that's negative 1 over 25. And then 1 over 250, 1 over x minus 5 dx. So don't know why I changed the order, but that's okay. So the 1 over x plus 5 is just going to be natural log of x plus 5. X to the negative 2 power rule is going to be x to the negative 1 over negative 1. So the negative 1 will change that negative to positive, and x to the negative 1 will just drop down to the bottom. And then we have another natural log here. And yeah, they kind of combined them in the answer. I'm not a huge fan of that, but it's not difficult with just basic log properties. I'll explain to you how they combine that to get this. That's pretty easy. If you put this, the one that's positive in front over here in the first part, and you have minus between the two, log properties means minus is division, just like plus is multiplication. So you see they both share a 1 over 250, so there's the 1 over 250, and we'll treat it as a plus. But this minus right here means that we'll have, the first one is plus, you'll have x minus 5 in the numerator, and then x plus 5 in the denominator like this. Because that minus is coming from the log property, which would make that subtraction. And, oops, well, that didn't affect anything, but now it's kind of bugging me that, just notice I forgot my plus C there, didn't I? All right, there we go. All right, terrific. Let's see number 30. All right, it's going to be another partial fraction decomposition. This one's actually easier than the other ones because it's 3 distinct linears. So the denominator, you'd factor out an x, and then the quadratic that's left then also factors. And you would get x minus 3 and x minus 5. So 3 distinct linear terms. So not the tricky ones where we have the quadratic, which I assume I have that probably coming up. I would hope I put that on here. Yeah, got to kind of cover all of our bases here. I wouldn't put repeated quadratic on the final, but the regular quadratic could be on there. So we have 3 ABCs, so nothing weird here. This one's pretty straightforward. So once again, we multiply by the common denominator. You see this A would have the other 2 denominators with it. B would have the other 2 besides x minus 3. And C would have the other 2 besides x minus 5. And so you come down here and then you plug in your test values, easy. Put in 0, gets rid of B and C, that enables you to get A. Put in 3, gets rid of A and C, where you can solve for B. And put in 5, gets rid of A and B, and you can solve for C. All right. So, and they work out to all be whole numbers. Obviously, we've even seen the last example proves that. But now I don't want the fractions to get too bizarre or anything like that. But these are all whole numbers, so pretty easy. These distinct linears are pretty easy. They're all going to be natural logs. 2 over x, 4 over x minus 3, 2 over x plus 5. Now this one didn't combine anything together, which is good, log-wise. So it matches answer D perfectly, so that one's not too bad. Now let's try to get a new challenge here in 31. So we have the denominator, we have x cubed plus 16x, so we'll factor out an x. So you have x times x squared plus 16, which x squared is plus 16. One of the terms they use is irreducible quadratic. It's basically a quadratic that has imaginary solutions. That's the easiest way to think of it. But x squared plus something is going to be the key, because that hopefully you don't think that factors. It always surprises me every once in a while in Cal 2 when someone does. Yeah, because that was x squared minus 16, or oh no, we had x squared minus something 2 problems ago. Yeah, then we would factor it one step further. It would not be this situation right here. We'd factor x squared minus 16, but x squared plus 16 does not factor. So whichever denominator we put first doesn't matter, but I put the x first, so I put an a over x, and then this quadratic always means it's the next letter wherever you are in the here, next letter times x plus the next letter. So if I started with a, that means this is bx plus c. Now this could have gone first and been ax plus b, and then I could have had c over x, and that would have been fine. That would have been okay. As long as you have it of that form, you know, this bx plus c or ax plus b or whatever, as long as it's like that, we're good. Alrighty, so I cleared out the denominators. Not too bad. Now I did a little different technique on this one. This is one I kind of showed in the notes a little bit, but okay, I multiplied this out into these terms, and I sort of left a step out here, but I'll say what it is verbally. I didn't leave the step out in my notes, so you could go back and look at it. But so you have these terms. So if you have ax squared plus bx squared, if that's going to equal 3x squared, that means a plus b would have to equal 3. So you're kind of like grouping the coefficients. So had I gone one step further like I did in the notes, I would have put parentheses around that. I would have said a plus b x squared like that. I would have written it that way. Then I would have said a, so then I would have equated the a plus b to that 3 right there. So all right. And then the x's. So obviously if you're missing any powered term over there, it'd be a 0, same thing. So if you have a cx over here and a 1x over here, that means if cx equals 1x, that means c has to equal 1. So we've got c. And then for the constants, we have only one. We have 16a, and we have 1. The left side only has 1. left side would only have one anyway, but 32. So that means 16a would have to equal 32. So that means a equals 2. Oh, then of course, so now that we know a equals 2, you can come back to this first one, and that means a is 2, b would have to be 1. So we have 2 for a, 1 for b, 1 for c. So we write this back out, and of course, once you have this, you can split this fraction up. So I have a is 2, so I have 2 over x, and then I have a 1 for b, so I have x over x squared plus 16. And then c is 1, so I have 1 over x squared plus 16. First one's easy. 2 over x would just be 2 natural log of x. Now, I didn't show the u sub part here, but I'll say it real quick verbally. This one's also going to be a natural log, because if you let u equal x squared plus 16, du would give you 2x dx, and then we would just divide both sides by 2 to make it 1/2. That's where the 1/2 is coming from, is dividing that by 2 to leave x dx. And now we just have 1/2 du over u, so it also produces natural log. Now this one without the x on top is arctangent. It's in perfect form for arctangent, no substitution or anything needed here. So the x would be your u, a would be 4, the square root of 16, and then so it's 1 over a tan inverse of u over a. So it's 1 over 4 tan inverse of x over 4 plus c, or arctan or whatever. And they're all plus, so it matches answer B perfectly. All right. Okay, let's move on into L'Hopital's rule. Let's see what we got here. So this one, this limit, as you put in 0, substitute 0, that means you have 0 over 0, which means it is eligible for L'Hopital's rule. And so the derivative of cos of 3x would be negative 3 sine of 3x, and the derivative of the bottom is 2x. Now there's a little star I put in there in my notes, obviously that was my indicating I was performing L'Hopital's rule. That's not mandatory. Put it there, but that was my sort of code instead of writing, use L'Hopital's rule next to each step, a little tedious. So we still have 0 over 0 actually if you put 0 in here, so that's no good. So we have, let's do L'Hopital's rule again. So the derivative of negative 3 sine of 3x would be negative 9 cos of 3x. Remember, chain rule, derivative of 3x. Same thing we did here. So it's negative 9 cos of 3x. Now we have 2, so now we're not going to get 0 over 0. And we put 0 in here because we have 2 on bottom, so cosine of 0 will be 1. And so then we have negative 9 times 1 over 2, so it's negative 9/2. Now, the next one, x goes to negative infinity of this. I'm mentioning that L'Hopital's rule is not necessary. I'm not saying it's not valid. It's just not necessary. You could do 2 L'Hopital's rules. So sometimes when it applies, it would not be that much fun to use if there's a quicker and better way to do it, which there is here. Yeah, I've talked about that in my notes. So you got to find, so look top and bottom carefully, find the largest powers top and bottom, and they're both squares. So when they're the same power top and bottom, regardless of negative or positive infinity, you just take the ratio of their coefficients. So it's negative 18 divided by negative 8. And that reduces to 9 over 4. So yeah, this was the same thing. If it was just x to the 20th over x to the 20th, you could absolutely do 20 L'Hopital's rules. You'd get a big gigantic fraction, but that fraction would actually reduce to 9 over 4. So, but you see, that would just be a terrible waste of time when this is just so much easier. But it does fall under the category of using L'Hopital's rule. All right, here's what's definitely a L'Hopital's rule. If you put infinity in there, that qualifies as infinity, and then sine 10 of infinity over infinity 0, sine of 0, 0. So that was one of the rules that we learned, infinity times 0. Now, before you think that infinity times 0, that just means 0. Well, when I say infinity times 0, that's loosely translated as while one part's approaching infinity while the other one's approaching 0. It's not exactly the number 0. It's approaching 0. So that's the difference. So it doesn't mean a lot of these do end up being 0. Here's an example of one that does not. Well, it'd be awful if you made that mistake here and fell right into this trap, just picked 0 as the answer for D. But now these kind of problems, when they're multiplication like that, 0 times infinity, you have to drop something down to the denominator. So that way we can either get infinity over infinity or 0 over 0. One rule of thumb is never drop natural log. Always leave it on top. Trig's a little bit different. There's some problems in my notes where we dropped the trig function and we didn't drop the trig function. This one we do not drop the trig function. Well, how do I know? Kind of from experience, but the good news is if you did drop the wrong one and your problem started getting worse and worse and worse, then you could know that you might want to go back and try a different path. So that's one clue. It's not going to probably make you get the wrong answer. It's just it might turn into a nightmare. This one works out real nice. Now, when I say drop the x, meaning, in other words, multiplying by x would be the equivalent of dividing by 1 over x. So when you drop it down to the bottom, you got to put it as 1 over x, because remember, this part right here has to equal what we started with. So dividing by 1 over x is the same as multiplying by x. Now, it's L'Hopital's rule, 0 over 0. So the derivative of the top, the derivative of sine of 10x will be cos of 10x times the derivative of sine of 10 over x. Now, I'm not going to take the derivative here because I'm going to show you a quick little way to simplify this if you don't take the derivative. And then the bottom, I just wrote the derivative as being 1 over x prime because these two primes are going to have a relationship. So actually, 10 over x prime, derivative of that, divided by 1 over x prime would actually be just 10. Because you can pull that constant out. That 10 is the same thing as saying 10 times 1 over x prime. So then the 1 over x prime would cancel. That just turns out being 10 right here. So now you have 10 times cos of 10 over x. I put in infinity. Cos of 10 over infinity. 0. But cos of 0 is 1. So 10 times 1. So actually you get 10 for this answer. All right, let's take a look at this one. This is the one where you have to do we're going to have to do a little log trick to it there with the exponents. These are the forms where you have either 1 to the infinity like we have here, infinity raised to the 0, or 0 raised to the 0. So what you do here is you use some sort of variable, not x or anything. I always use y here, but maybe you want to use z or something. Who cares? Doesn't matter. Just don't use x. So I'm going to log both sides because we need that exponent to come down. So when you log both sides, I did this in the notes too. By definition, the limit of a log is the same as the log of a limit. So it's acceptable for me to log this, inside the limit part. The ln does not have to go outside the limit. And so that's why this is okay right here. So this 2 over x, I just left the 2 on top and the x on bottom. I mean, yeah, you could have written 2 over x in the numerator, but the x kind of needs to drop down anyway, so I went ahead and just did it first step. So now we have this. So we have 2 times ln of e to the 8x plus 5x over x. So now we're going to do L'Hopital's rule. Now the derivative of the bottom is 0, but what's going to happen here is that because, we're taking the derivative of natural log, that means we have, du over u. So I went ahead and just dropped the u part down to the bottom. So the only thing that would have been there is a 1 anyway. So the derivative of e to the 8x plus 5x would be 8e to the 8x plus 5, and then over the u itself. So that's the du in parentheses. That's the u on bottom. All right, so as x goes to 0, and we won't have to do any more steps. So we just plug, well, one more step as far as no more L'Hopital steps. Plug in 0, 8 times e to the 8x will be 8, because e to the 0 is 1. 2 times 8 plus 5, so 2 times 13. On the bottom, e to the 0 is 1. 1 plus 0 is 1. So you have 2 times 13 over 1, which equals 26. But 26 is not the answer to the problem, because what 26 represents is ln of y equals 26. But we need to know what's the value of y, because y is how we defined our limit. So no problem. The last step on these, all you have to remember to do is just take your answer and say e raised to your answer will be the answer. So if this is 26, that means the answer will be e raised to the 26th power. So y, which is our limit question that I'm trying to find. So if y equals e to the 26, that means our limit equals e to the 26. And there it is, answer A. So don't forget to take, when you work this out, that your answer is always e raised to that, whatever that number is. So we have limit of x raised to the sine of x as x goes to 0 plus, shouldn't have to worry about that plus too much. I want to treat it, sometimes that's necessary if you're worried about, if you're dealing with functions like square roots and natural logs and things where, you don't have your functions undefined on certain places. But here, it's probably not critical. I'm basically using a principle in Cal 1 that says that if you treat this just as 0, if you find what I call the regular limit, it's not really a mathematical term, but the limit as x goes to 0, that means that, and you get an existing value, that means the one-sided limit, both the plus and minus limit, have to be the same as that limit. So I'm kind of, even though I wrote the 0 with the plus there, I'm sort of ignoring it, in the sense that if I just work it out normally and get an answer, that has to be the answer for that one. So I had to do the log thing, so I let y define it, did the log thing, brought the sine. So I essentially inserted it was ln of x to sine x, so I brought the sine of x down in front of ln of x. Now, so we have ln of x, and then so since that's times sine of x, I had to rewrite that as 1 over sine of x on the bottom, which is just essentially cosecant. So, I could have immediately wrote cosecant, some point change the 1 over sine and make it equal cosecant. So it's ln of x over cosecant, because we never drop ln down to the bottom. So we had to drop the trig function. So now we do L'Hopital's rule. The derivative of ln of x is 1 over x. So this is important that we know the derivative of cosecant x is negative cosecant times cotangent. And let's see what we have here. And so I rearrange these algebraically. So what happens here is that Cosecant is 1 over sine. Cotangent's cosine over sine. So basically on the bottom you have cosine over sine squared divided by cosine. So you flip it over and sine squared ends up being on top. And I just brought the negative from the bottom up to the top. So the x came down and then joined the cosine that comes out of this cotangent. So you have x times cosine on bottom. Now you might discover other ways to do these. Sometimes I've done them. These ones that are, I would say, a little bit more complicated with the trig. I've seen, then all of a sudden I'll look at it and I'll see a different way to do it some other time. In fact, I do see a different way to do this one. I'll write one little note there for you here in a second. But anyway, I did L'Hopital's rule one more time because at this point I have 0 over 0 if you put 0 in there. Got to be careful with chain rule. With derivative of sine squared, you bring down the 2. It'll be sine to the first times the derivative of sine, which is cosine. Then the bottom, product rule. And you product rule f prime g, you'll get cos of x minus f g prime x, negative sine of x. And then I put 0 in. On the bottom, I'll have 1 minus 0, which is 1. So that's good. We don't have 0 on the bottom anymore. It's okay to have 0 on the top because 0 divided by 1 is just 0. It's when we have 0 divided by 0 that we have to do L'Hopital's rule. So that's just 0 over 1 is 0, but remember 0 is not the answer. Don't pick answer B here. The answer is always e raised to what you get there. So we have to say it's e to the 0, which is 1. But the little trick I was going to show you here, if I can find a little space, come up here. And if you remember this goes back to Cal 1. Of course, obviously this one by itself could be derived real quickly using L'Hopital's rule. But Cal 1, we talked about this. The limit as x goes to 0 of sine of x over x by definition is 1. I mean, there's a proof for it if you want to see it. But L'Hopital's rule makes it real easy to derive. Well, anyway, the point I'm trying to get is I could, and limits are a little bit different than derivatives in the sense that you can kind of work with limits as limit of a product as the product of individual limits, which is not true for derivatives. So let's say if you have the limit of f times g, you can treat that as a limit of f times a limit of g, but we know that's not true for derivatives. You have to use a product rule for derivatives. But anyway, you could bring out a limit of sine of x over x, which is just going to go to 1, and then that would just leave you a negative sine of x over cos x, and you would put 0 in, you would get basically negative 0 over 1, and you still get 0 that way. So that's another way you can come up with it.